Hey everyone. So I'm going to give a talk today, short 20-minute talk about validation, equivocation, and Byzantine fault tolerance. It's really a talk about how to avoid doing Byzantine fault tolerance in certain contexts. Byzantine fault tolerance analysis is a kind of analysis of distributed systems when you have an assumption that some of the terms might be corrupted in some unknown way. So I'm going to give a talk basically about my approach to doing Byzantine fault tolerance that I've developed in CVC Casper for over the last years. It was originally planned on being a highly technical talk, and now I made it into tech intuition talk. And so it's going to be somewhat technical, but I'm going to try to keep it about the intuitions, and I'm not going to write almost any math. So So hopefully by the end of this talk, you'll have an idea of how you can avoid doing Byzantine fault tolerance when you're analyzing distributed systems. So first thing I want to talk about is state transition systems. I'm going to build up a kind of language in which we can talk about validation and equivocation in terms of state transition systems. So let's start with just a normal traditional kind of state transition system. So a normal state transition system, we have some kind of set of states, and I'm going to call them here. I'm going to a little hat, which means they're proto states. So this is like our big set of states. This is kind of where the protocols live. They have states, and then there's something called a state transition function, which I'll denote here as tau, and it takes states and gives you states. So this is a state transition function. And you can imagine inside this set, we have all sorts of different states. And then each state has a transition. Let's use the arrow tool. Each state has a transition to another state. And this is basically just given by this transition function. So the transition function tells us kind of which states map to which states. And so we can kind of understand in some way a trace of a protocol in terms of kind of following these arrows. So like this is a partial trace of the protocol. This is a partial trace of the protocol or of this transition system. And so, but we're not going to be really interested in all traces. We're only going to be interested in some of them. Specifically, some states are going to be initial states. So I'm going to circle the initial states here in blue. Some of them are initial states, and we're only really concerned about traces that start in the initial states. And so like normally we're going to consider, for example, this trace might be a protocol trace, and this trace is a protocol trace. These are kind of the execution of the protocol starting from the initial states. So given this set S hat of states, we have a transition function that maps all the states to one another inside here, and then we can think about the initial states and then which of these which traces start from the initial states. So that's all good, but the problem here is that this is a deterministic system. Every point only has one arrow going out of it, and that won't really do us too good because so I did screw up the drawing there because I had two arrows out of that point. To actually get more than one arrow, this function won't do, and we're going to need something else. So now I'm going to tell you a little bit about a labeled state transition system, where instead of just having a state mapping to a state, we have a label and a state mapping to a state. So this is a labeled transition system. It's kind of similar to the previous one, only now we get to have the option of having two arrows from a particular, out of a particular state. This kind of corresponds to a non-deterministic transition. You can kind of go from one of these states to either one of those two, and they will maybe have a different label. This one maybe has like a label L1, and the other one maybe has a label L2. Anyways, my font's a little big here, but you can kind of get it. Basically, with one function, you map states to states, and you only get one state for every state. With a label, we get, for each label, we'll have a state from each state, and then it might be possible from some states to have more than a couple of future states based on this this kind of label. So the label for one of these transitions will be different than the other. So that's good. Now we can express kind of non-deterministic protocols. Still, we're kind of assuming that there are some initial states. And then we can talk about traces starting from the initial states. And now we have kind of choices. We can go kind of this way, or we can go this way, all from the same initial state. Whereas previously we were kind of stuck on a single path from any initial state. So that's cool. So this is neat. I mean, we can use labeled state transition systems to talk about all sorts of different computational phenomena. And it's a pretty cool system. However, it's all very serial. There's no concurrency. There's only one program term here in this state. And so we'd like actually to have something a little bit more. Specifically, we want to have messages being sent and received so that we can have a bunch of these running in parallel, kind of talking to each other. So I'm going to define something else now here. So rather than just a labeled transition system, now I'm gonna talk about a labeled transition system with messages. So our transitions, now we're gonna have a label still and a state like before, but now we also have a message. And then we also will produce a state and a message. Oops. With each one of these transitions. So the transition, rather than being just labeled with a label, they're also going to have a couple of other labels. So every transition is going to have basically so let me try to make this text out here. So you're gonna have a label and then a message in and a message out. Great. So every state. So every transition is not only going to have a label as before, but it also has a message that comes in and a message that comes out. So this is cool because it lets us understand not only states, but also this, somehow we have this notion of messages now. And so what I'm going to try to do now is we're going to consider multiple of these kinds of transition systems in kind of composed. So now this is getting closer to what we might understand in a distributed system. So we have initial states and transitions for each of the components. And then the components have these messages that they can receive and send with certain transitions. By the way, I want to mention that these messages are optional. So, you can imagine that not every transition receives a message and not every transition sends a message, but some of them do. And then you can imagine that the messages that are received actually can't be just any message, but they have to actually have been produced by one of these terms. So, you can't just receive any message. You can't just transition as with a label transition on any label that we want. To transition on this arrow here, we actually have to receive the message M. So in this setup, we have basically, in some way, you can imagine a very loose, but I mean, and now I'm stating it kind of loosely, but actually when we do this formally, it's very tight, but a very loose kind of description of distributed systems in terms of different state transitions available to different nodes. And we kind of will observe that in some way, these executions won't be independent, possibly because they might receive messages from each other. So for example, let me just, I can indicate this with a line perhaps. So maybe, you know, perhaps maybe this message here is received here. Maybe a message is sent from that transition and is received in this transition, and therefore kind of allows that transition to take place. So, and then, you know, similarly, maybe it also is received here by this node. So basically, you know, this kind of describes a distributed system where we have these components with known states and messages and labels that we have. But when we're talking about Byzantine fault tolerance, we kind of have another case. We have a case where basically we have some other terms, maybe say these two terms here, rather than being the terms that we would kind of expect. We have kind of unknown terms here. We basically have some terms here which we don't know anything about. Actually, we have these terms which have unknown states, produce unknown messages, have undefined behavior, and these are kind of called Byzantine nodes. And Byzantine nodes are they're undescribable. You know, you can't really say what a Byzantine node is doing because it can be doing anything. That's kind of the definition of a Byzantine node. It's untyped, and similarly, interestingly, Byzantine nodes can send messages to correct nodes and change the way that they transition. And so now all of a sudden our analysis of how, you know, send nodes to each other, and all of a sudden the analysis of how these how the protocol evolves starts to become a little more interesting and questionable, because, you know, in some way you can imagine these Byzantine nodes can send any message. And so the amount of transitions that are available here are much greater than previously, where we only allowed, say, only messages that were produced by these other terms. So how do we deal with this? What are we going to do to understand the behavior of our protocol in the context of these unknown terms that can basically do and send anything? Well, I'll tell you what we're going to do. We're going to introduce this additional kind of thing on top of this transition system, which is a validity condition. So a validity condition you can think of as a subset of L cross S hat cross M. So this is basically, it says, oh, look. So the idea with the validity condition is before transitioning on a particular, before transitioning at a particular arrow, we have to check the validity condition for the label state and message that we're about to transition to, because it'll be kind of invalid to make that transition otherwise. So we augment our transition system with this additional thing called the validity condition, where you know, the coloring on the transitions for which ones are valid. So then we go back here, and now rather than you know, now kind of assuming we have this valid thing, it's not going to be the case that the Byzantine nodes can, I mean, they can still send any message, but it might be that that for some of them, it's invalid actually for the protocol following node to receive. And so for those messages, the ones that are invalid to receive, it's going to be, the Byzantine node isn't going to be able to use that message to make a node transition. So, so then we're going to do another trick, actually. So let's imagine that we were here, where we were initially, where we're not considering any Byzantine nodes and only considering these protocol following nodes. What we can do is we can think about, okay, what traces here are actually protocol. Like some of them are going to be protocol in the sense that they are reached from the initial states by these terms when they're composed with these other correct terms of them. So some of these traces are going to be reachable, and when they're reachable, we call them protocol. So if they start from initial states and you can get to it by protocol transitions that are not just valid, but so originally we weren't talking about validity, but now we are. So we're going to, these ones by virtue of being reachable are valid, but they're reachable specifically using messages received from these other terms. And so we can look at these traces and say, okay, these are somehow the ones that we should be reaching, but which, and so we can say, like, let's try to make our valid condition only allow our terms to reach these states. And then what that will do is it'll restrict the ability of the Byzantine nodes to push our protocol nodes off of these paths. So our protocol nodes will specifically only ever transition on valid paths. And so these big, bad, unknown Byzantine nodes will not be able to push our terms off of the valid traces. Specifically because, the term will, when receiving a message that isn't possible for it to receive in a normal execution, will just reject that message because it's not valid. So, this kind of corresponds pretty normally to the notion of validation that we have in the blockchain space. Like you receive a block, you check if it's a valid block. And if it's not a valid block, you don't transition with that block. Pretty simple. But somehow what I'm pointing out here is that this is going to restrict the way that the Byzantine nodes can actually cause these terms to transition. Great. And so in some way, this is the beginning of our strategy for avoiding Byzantine fault tolerance analysis. Because now, although these undefined terms can send any message over, only valid messages will cause transitions. And as a result, it's almost as if the Byzantine nodes are restricted to only sending valid messages. So that's good. And we might feel like we're done. But actually, there's this interesting thing called equivocation, where this Byzantine node might send two messages here, one to one term and one to the other, M1 and M2, which, although they're each valid messages, there's no trace for a correct node that produces both M1 and M2. So for example, M1 might be a message that says, hey, I'm deciding on 0, and M2 might be a message that says, hey, I'm deciding on 1. These messages both kind of have to exist, or consensus protocol in some way, and so they're valid, and it has to be possible for nodes to receive them. But the thing that'll happen here is that one of these nodes will go down one transition, and the other one will go down a different one in a way that wouldn't be possible actually normally in the original trace that we were talking about. So it may be in the previous system that the terms always went the same trace because they're all kind of coordinating together and there wasn't this equivocation. And so the traces that they took were kind of consistent with each other. One node decides 0, the other one should decide 0, 2. But in the context of this kind of equivocation behavior, it might be that even though there's only valid messages, these terms can basically end up having inconsistent decisions or different traces that don't behave in the same way as they do without Byzantine nodes, because basically, these messages that they're receiving, these equivocations are valid messages, and therefore they get through our validation filter, but it's somehow impossible in a normal protocol execution for a correct node to send both these messages M1 and M2. They're kind of, they're kind of inconsistent messages. I don't know how to describe that. They're kind of inconsistent messages. They can't really both be sent from the same trace, and that kind of makes it quite problematic for us because we were trying to restrict the traces in a way that stops these protocol following nodes from exhibiting behavior that where we have to consider this Byzantine behavior. But now actually we have actually restricted Byzantine nodes quite a lot already by having them only send valid messages. And so I kind of came up with this neat trick, which kind of lets me just forget entirely about these Byzantine nodes and instead consider just these kinds of correct protocol following nodes by kind of bending a little bit one of the assumptions that I made earlier implicitly. I kind of made this assumption that to receive a message in one of these terms, it had to have been sent by one of these previous terms, or by one of these other terms previously in the same execution. But actually, it turns out that assumption is if we weaken that assumption, if we get rid of the assumption that the messages that are received by these terms had to have been previously sent by these terms, and instead weaken it to had to have been sent by one of these nodes in some trace, not necessarily this trace, but in any trace of the protocol that's possible. Not necessarily the one that we've experienced here, but one that's kind of, you could think in an alternate universe. Like initially, you can imagine all these terms start with these initial states, and there's different ways that it could evolve. And one of those paths, M1 is produced, and then the other, M2 is produced. Well, if we just allow M2 to be produced in the path that includes M1, then we're kind of exactly allowing this equivocation behavior. And so the story here basically is that by allowing messages to be received not just from within an execution trace of this composite protocol, but also from between execution traces of the same protocol, we can kind of introduce all of these equivocations, all of this kind of bad behavior that the Byzantine node was able to exhibit to correct nodes, but which it kind of got through the validation filter. It is now going to be expressed in terms of these well-defined terms, with this additional weird property that they get to send traces to each other. Sorry, they get to send messages to each other on traces that are on different timelines. So if in one timeline, we decide 0, and another timeline we decide 1, when I'm composing them in this new special way, I'm going to allow messages to be received on the first timeline, even if they were just sent on the second timeline. So this kind of trick, it basically allows me to receive all possible messages from all possible terms, not just the ones that were experienced on this trace, but ones that were experienced on any trace. And so then similarly to before, how we said, okay, let's consider these 6 things together and what terms they touch. And then we kind of make those validating. We make the protocol validating by restricting the validity condition to make it invalid to transition to any term that isn't reached by these 6 terms when they're together. Now what we're going to do is something slightly more, basically exactly the same, but slightly different, because rather than assuming that messages that have been received have to have been sent, we can receive messages that weren't even sent in this trace, but were sent in some other parallel universe, but also by these 6 terms. And so we can do exactly the same thing with a different message model that allows these equivocations to be sent kind of between timelines, and do exactly the same process of considering only the traces that are reachable in this composition of these terms, where they're allowed to send messages to each other also from across timelines. And so what that will let us do is it'll give us all these traces for these terms that are valid, and those traces are going to include everything that can be reached by receiving equivocation. And so, sorry, one second. Yeah, and so basically, what this is going to let us do is we're going to be able to see all of the traces that are a result of receiving all equivocations in all possible ways. And